We're going to have the student session 1, which is around network and security. And the first talk is given by Dorsa Sadigh. She's a PhD student at EECS department at University of Berkeley, California. Please welcome her to start her talk.
All right. Hi, everyone. Thank you, Sarah, for the nice introduction, and thanks a lot for inviting me here. So I guess I can start. People are getting in. OK. Where's the pointer? All right. So today I want to talk about learning and safe control for human cyber-physical systems. So let's get into the details of that. And this is work that's funded by ND-SEG Fellowship, ONR, and NSF. All right. So when we talk about human cyber-physical systems, we first need to define these systems, right? What is human cyber-physical systems? These are basically cyber-physical systems that have software side and a physical side that interact with humans. And there are a lot of examples of them, including, let's say, robotic surgery or interacting with drones or like playing with quadcopters. That's getting popular, right? And basically the autopilot system, semi-autonomous driving. So all these systems have something big in common. And that is they have human as part of their control loop or as part of the environment or as part of the system. And one big important thing is they're all safety critical. So it's important to have a good model of the human for these systems and a good model of the autonomous controller and make sure the interaction between the autonomous controller and the human is working out fine for all these systems, right? So it's really important to trust our surgeon that's using an automatic surgery like task. For the rest of this talk, I'm going to talk about semi-autonomous driving. So I'm motivating it as human cyber-physical system, but the rest of this talk is basically focused on cars. But everything I say, most of the things I say, does apply to all the other systems too, but that's going to be a separate talk. So let's get into cars. So cars, the first thing that comes to our mind is Google. Google is doing this driverless car idea and is proposing that we're going to have fully autonomous cars in like soon, pretty soon. So if you look at Google's approach and how they started, this was around beginning of my PhD. They started thinking about semi-autonomous driving. Anthony Lewandowski gave a talk at Berkeley, and I specifically remember he was talking about this switching control, this idea of we have an autonomous car, and if autonomous is doing highway driving, and if you want to get off highway, then you want to ask the human to come and take control. So we're going to do a switch control based on the map and based on the location, and we have Google Maps, and those are pretty accurate. But then all of a sudden, in May of 2014, Google decided to completely change the idea of semi-autonomous driving and move towards autonomous driving, fully autonomous driving. They got rid of the steering wheel, they got rid of the brake, everything. You just put a human in the car, and the car is going to drive itself. So they eliminated the human, and the main reason they eliminated the human was it was really difficult to model humans. They couldn't model humans, and they couldn't rely on humans and ask humans to come and take control. So this was the Google's cop-out, I would say, or transition. But one question that I always ask is, why don't we learn from the avionic industry? They have been doing this from 90s. There's a lot of work on the avionic industry and how humans come in and take control in aircraft. So we have really good aircrafts these days, right? We have autopilot systems that does all the landing and taking off and everything automatically. But we still put a pilot there, right? Why do we put a pilot there? Because there are situations that the pilot can take control and save us. An example of that is the Airbus 320, and this is 2009, where both of the engines were failed because a flock of birds just attacked the engine. And then the pilot basically did an emergency landing and saved everyone. And this was on Hudson River. And this is not just a single example. If you just do a basic Google search, you find all these crazy emergency landings that the pilots can take control, and they have better perception than any autonomous system and can figure out and help us and basically save the day. And sure, there are crazy pilots. So this was last year, Germanwings. The co-pilot destroyed the plane, and this was deliberately done by the crazy human. So sure, when we bring in humans, we have crazy humans too. And then more important than crazy humans and worrying about crazy humans is the problem of mode confusion. So if you put a pilot there, and the pilot should know what the control system is doing, right? So this was also another example of a crash. This was a Gianna flight that crashed at SFO. The problem was the pilot didn't know what the control system was doing. So I guess we can conclude that we need to put humans in these systems, but we need to make sure that the human has full information about the control system and can take over control if something goes wrong. So that's basically the avionic work. And going back to the Google side of things, So they decided to do this approach, right, in 2012, 2014, that was the goal. But now, like, since May, they're doing these monthly reports of the type of crashes that they've had. And in only, like, a few months, they've had, like, 11 crashes. And in all these crashes, they're rear-ended, and Google is basically saying it's the other car's fault, it was not our fault. But, like, I drive every day, and, like, why am I not, like, getting rear-ended 11 times in a year? Not even 2 months. In a year, why am I not getting rear-ended? And the problem is Google is trying to put this autonomous car in a world full of these humans that don't follow the rules of the book. They're completely stochastic, they do crazy things, and it's really difficult to put a fully autonomous system and make it interact with the stochastic world around it. So even though Google has tried to eliminate the human in the car, there's still humans outside of the car. There's still pedestrians. There's still, like, other cars driving around us. And we need to deal with those humans. So today I want to talk about 2 quick things. Like, there's a lot of, like, problems and research done, in this area. But I'm going to focus on 2 things. One is, how can we deal with the humans that are outside of the car? And and even if we eliminate the driver, how can we make sure that we have good models of these humans and we can affect them? And the second thing is, sometimes if you look for this too safe a strategy, this provably correct strategy, the unsafe outcomes can come up, and it's not necessarily the best thing to do. And that's why we need human intervention, and that's why we need to, like, carefully do this human intervention in those scenarios. All right, so let's get into the first one. It's difficult to deal with humans. What can we do with these humans outside of the car? So this was a recent project that we started doing with Shankar Sastry and Anka Dragan and Sanjit Seshia. And the idea was we want to plan to leverage effects on human actions. So what does that mean? We have drivers on the road, and these drivers don't drive in isolation, right? We have all these drivers that can be affected by the autonomous cars and all the other cars around us. And the idea here was, can we plan for the autonomous car so it can affect the human drivers? Can we deliberately make the human drivers do something? So the point of this project was to show that we can do that, and we can plan for the autonomous car to do that. And if you do, like, what is our hope or our goal here? We basically want to be more efficient and more communicative if we know we can affect the humans, if we know that I can affect this other driver. So in all my figures, the yellow car is the autonomous car. The red car is the human-driven car. So in the first figure, this one, let's say that the autonomous car wants to change lane. If it wants to change lane, it could either wait for the red car to pass and then change the lane safely and slowly, or it could be more aggressive and actually cut in front of the red car. And if that's my grandma driving, I would actually cut in front of her because I know how she's driving. I have a model of my grandma driving, and I'm going to, like, cut in front of my grandma because I know she's going to be slow. So the idea is, can we have autonomous cars that do that? Can we have autonomous cars that are not as conservative? And then the second example was actually interesting. This is when you have 2 cars getting to an intersection, and let's say the autonomous car wants you to cross first. It doesn't want to cross, it wants you to cross first, and it wants to signal you to cross first. So the control that we found out automatically was the car actually backs up and, like, hovers there, kind of like trying to signal you that you should go first, and this was automatically generated, and that was really, I was, like, really happy with that result. All right, so let's get into some of the details of how we do this. So the way we model this is as a 2-player game between the human and the autonomous agent. And our goal is we want to find the control actions of the autonomous. So we want to find the optimal actions of the autonomous, which is going to be a maximizer of sum of rewards of the autonomous car, right? So what is this sum of rewards? The sum of rewards is my car shouldn't crash and should follow all the rules and be a good autonomous car. And in addition to that, it should, where is that? It should make sure that it's affecting the human. So that's why it has actions of human here. So we want to affect actions of human. And what are these actions? These are the optimal actions of human. And the optimal actions of the human, what do they depend on? They depend on an initial state and actions of autonomous. So here I'm making an implicit assumption that this actions of human depends on the optimal actions of the autonomous car. And if I am talking about human-robot interaction, like, people get mad at me because of this assumption, because here I'm assuming that bounded rationality does not exist. Because for a lot of human-robot interaction, if I am, like, doing something with a robot arm and the robot arm is in front of me, I assume bounded rationality. I assume that I don't know what the optimal actions of robot is, right? I'm doing something, I have no idea what the robot is going to do. So I can't assume that I know the optimal thing that the robot does. Because I don't know the robot's intent, and it's a robot arm. How do I know what it's going to do? But I would argue that for driving, it's actually the case that you know the optimal action of the robot. So if the car cuts in front of me, I know what the car is doing. I know the car is cutting in front of me and what the next steps are. So it's actually a fair assumption. And in addition to that, we have bounded time horizons. So for bounded time horizon, it's okay to choose optimal or suboptimal. It's not making that much effect. And it's actually not changing our results much. So in our results, oh, it's 10 minutes. In our results, we didn't have too much issue on that. All right. So we have actions of human, right? So we need to find the optimal actions of human, and the way we find optimal actions of human is based on some reward function of the human driver, right? And basically, it's a maximizer for that, and the way we solve this is by using some gradient-based iterative method. So it's actually not easy to solve this optimization. We are doing this in continuous time, continuous state, continuous input. Making this real time was actually a big challenge. And it's difficult to solve this, so if you want to learn more about this, we can chat offline. And one big question is, what is this reward function of human? We are modeling the human using maximum entropy inverse reinforcement learning, which is a common approach used in human-robot interaction. And the idea is, if we have the actions of human are going to be proportional to exponential of reward of human. What does that mean? That means that if if my action makes me end up in a state that's better, it has to be exponentially better. I have to make it exponentially better. And then the rewards are going to be a linear combination of a set of features that we have. And these features include, I want to stay within the lanes. I want to make sure that I don't, I'm inside my own lane. I don't crash any cars. So we use Gaussians around each one of the cars for the features. So let's get to some of the results. All right, so here we have the autonomous car, the yellow car. The human-driven car is the red car. And we want to make sure that we want to affect the red car. We want to make the red car slow down. And the data that we've gathered is from user studies with 10 different all right, so we have more time. OK, good, more time. So the data that we've gathered is from 10 users. So the orange data corresponds to the humans that are affected, and this is the speed of them. So the speed, you can see that there's a sharp drop. The human actually did slow down by our actions. And then the gray ones are for the ones that the human is not affected. It continues keeping its own speed. The second plot here is the latitude, so the position of the human-driven car, and the position kind of becomes constant in the orange case because human is affected. The purple plot corresponds to our optimal human model. So if the users did follow the optimal thing, then the purple thing would have happened. Yeah, and then as you can see, the speed of the human does slow down. And you can say that this way, the autonomous car is more efficient. So here, our sole goal was the autonomous car should affect the human. That's the single thing we wanted to do. But we can say that it might be more efficient because there might be a baby or like a truck or something in front of here. And it might be safer for the autonomous car to actually affect the human, knowing that it can affect the human. This is the next example. The next example is the communication example I was talking about. So here, the car actually backs up. The autonomous car backs up, telling you that you should cross. And in the plot, this is the center of the intersection. So the trajectories that go around it these are the trajectories that the human crossed first. These are the trajectories that the autonomous crossed first. And this shows the reward that we calculated. This is that reward of autonomous. And it's a heat map of the reward of autonomous centered around the human-driven car. So the autonomous car wants the human car to cross first. That's why it has higher reward for going upward. So overall, we can be more communicative. We can be more effective using this approach of knowing that we can affect humans. And we should use that. We shouldn't be as conservative as Google or all these other car companies right now. So the second thing I want to quickly get into is this idea of situations in which the two safest strategy does not exist. If it doesn't exist, what should we do? So we have an autonomous car. An autonomous car is interacting with all these human cars around it. And we have a model of these human cars, a stochastic or whatever model of these human cars around us. And if we have those models, sometimes we just don't have any options. We can't go anywhere. Like if we do anything, these cars are going to run in front of us based on our models. So what can we do? How can we solve this problem and still be safe? All right. So the idea here was we start with a goal. Let's say our goal is making a left turn. That's our goal. And we have some sort of environment model and some sort of human model for stochastic, deterministic. And we give this to our favorite controller synthesis tool or use our favorite control algorithm. And then if we get realizable, we get autonomous cars. We have Google cars, perfect, everything is great, everything is autonomous. But there are a lot of cases that we come up with unrealizable, meaning that there is no control that can be safe and that can satisfy everything that you told me from the beginning. One example that I really like is this idea of doing unprotected left turn, because this happens to me every day. This is like Shattuck Avenue. This is university. So what is unprotected left turn? This is your car. You go in the middle of the street when it's green light. You just wait there for the queue of cars to pass, and then after that you make your left turn. And a lot of times the light turns red and you're just like waiting there. And we as humans are really good at handling this, because if I'm driving that, I'll be like, I don't make an eye contact and be like, wait, let me do this. Or I would be like, whatever, I don't want to do this. I'm going to change my objective, go straight, make a left turn later, make a right turn instead. So we as humans are really good at dealing with this type of infeasibilities. And we either change our objective or we violate something, but we're still safe, like we don't crash, right? And I just recently found out that this is called, in Pittsburgh, this is called like Pittsburgh left. People from CMU might know this. So what they do is they don't even wait for the lights. They, when the light turns green, they just immediately make the turn and don't even wait for the queue of cars to pass. So this is dangerous, but this is what people do in Pittsburgh. And this is not Pittsburgh, this is Arizona. Everyone points out that this is Arizona. Yeah. So it was interesting to find out that Pittsburgh left exists. And yeah, so going back to our optimization, what we do is we solve an optimization problem. We have a cost function on our trajectories, and we want to be safe, subject to knowing our human model, subject to knowing an environment model, and subject to a set of bounds on control inputs and states. So this is going to be our optimization. And the way we solve this optimization is using receding horizon control or model predictive control, which is fairly used in autonomous driving. So for the case of making an unprotected left turn, we have our goal of reaching some state with minimum control, and we want to have a minimum distance between the cars, and we want to obey traffic lights, and we want to stay within road boundaries. And we have a set of bounds for acceleration and velocity. The way we represent these is using this language that's called signal temporal logic. This is used in formal methods, and it's just like a high-level language for expressing each one of these properties. And what G means is globally. So globally at all times, from 0 to infinity, I have these bounds. And everything else, we express it in signal temporal logic as well. So just to formalize it a little bit more, we have this cost function, and now we want to say our trajectories, our finite horizon trajectories, are going to satisfy a signal temporal logic specification, which is phi. All right? So in this work, what we did was we had this temporal specification, and we can represent the temporal specification as a mixed integer set of mixed integer linear programs. And that translation, I can talk about that later. But there is a translation from signal temporal logic to mixed integer linear programs. And we have linear constraints now, fi is less than or equal to 0. And there are a lot of cases, let's say the unprotected left turn example, that this becomes infeasible. So if I give this to Gurobi, if I give this to my best optimization tool, it's going to come up with infeasible telling me that, oh, I couldn't do this. I went in, and then it failed. So what we decided to do was be able to kind of diagnose and repair what was the cause of the failure. Why did we fail? And the way we do this is similar to any other optimization algorithm. What we do is we add slack variables. So to the linear constraints, we're going to add a set of slack variables and make sure that those slack variables are positive. And we are minimizing the L1 norm of the slack variables. And the reason we're minimizing that is we want to find the least fixes, the least number of causes of failures, basically. So this is going to, if something fails, then we are going to get a non-zero slack to that specific constraint. And this kind of is going to pinpoint the specific thing that caused the failure. And then we translate back to signal temporal logic. So for this example, we translated that back to signal temporal logic. We found out our bounds for the acceleration and velocity were the things that caused the failure. And we found a repair for it. So the slack values can help us find this repair for the acceleration and velocity. And we found a repair, and with the repair, we have a trajectory. Everything is fine. But what is wrong with this? The thing that's wrong with this is the acceleration went from 1 to 11. So we automatically found out we should do Pittsburgh left. Automatically found out the best thing to do is to do Pittsburgh left. And this might not be the safest thing to do. That's why if we go back to our diagram, so we go to the controller synthesis thing, if it gives us unrealizable, we diagnose the failure in our algorithm. And then we go to the human. We ask the human, is this a repairable thing? Can I do that? And if we can do that, we go to the controller synthesis. We call it repairable. We have autonomous control, Google car, perfect. And if not, we ask the human to come and take control. We need the human to come and take control or either violate something or do something, fix it. And there's a lot of work doing on how to do this intervention, and I'm not going to get into that, but there's this problem of humans' reaction time or having human models or figuring out when to ask the human or what sort of information to show the human to take back control. So I think I'm on time, yeah. So to summarize, I talked about two things. One is to leverage effects on human behaviors, making sure that we can affect humans. And so now that we can affect humans, can we be more efficient? Can we be more communicative by affecting the humans? And the second thing I talked about is we need systems that are self-aware and that can ask for human, that can automatically ask for human intervention and give some sort of repair ideas to the human so human can take control. For future directions, we are looking at the smoother transition to the human and having good human models. And also, we are looking at uncertain environments. This is the work that we have already started with people at Microsoft Research using uncertain environments and being able to being able to do controller synthesis from signal temporal logic under uncertain environments and under Bayesian classifiers. All right, I just want to thank you, my advisors, Shankar Sastry and Sanjit Seshia, and all the awesome people I worked with during this project. Thank you.
Okay, thank you, Dorsa. We have time for a few questions, if you have any.
So you called it a two-player differential game. What is the utility of? I didn't catch that.
So the reward function. So the utility is going to be the sum of reward functions for the autonomous car. That's going to be, I don't want to crash, like things of making sure that the car actually drives right, and affecting the human. So the idea was I want the human to slow down. That's going to be part of my utility. If you don't put that in, if you say that I want to reach my goal faster, based on my model of human, it actually tries to affect the human, make the human slow down, so it reaches its own goal faster.
And did you then solve the HAI equation to get the optimal control?
So we are finding the optimal control. It's not HAI, but we are finding the optimal control in that two-player game. We're using a different approach. It's a gradient-based approach, and assuming that our trajectories are suboptimal. The trajectories gathered from the human. So the data that we've gathered are suboptimal in driving. It's not exactly HAI, though. We are doing the optimization to find UR star. So we are finding the optimal solution for the autonomous, assuming that we have a model of reward function of human. Yeah.
Any more questions? Actually, I have a question myself. Are there any location-specific or location-related measures or considerations in the design of the control of these machines, like the?
No, we're not including that. We're not including any location-based.
For example, big cities, you know that people are more aggressive. In smaller cities like here, you would wait like.
So that should come into the human model. So far we're using a very simple human model, but those things should come into the environment model and human model. So it's not exactly location-based. It's based on how aggressive and how adversarial my environment is, or how aggressive my human is. It's my grandma, or if it is someone aggressive that's going to cut in front of me. Yeah, so one thing we are looking at is basically being able to explore these human models, being able to explore these driving styles and take that into account our algorithm, basically.